Hello everyone, welcome to my YouTube channel of the subject Basic Electrical Engineering. Myself Pankaj Shah, and previously you were watching the videos on AC circuits. So basically in AC circuit we have seen series AC circuits, and in series AC circuit we have seen one condition, that is the resonance condition in that series AC circuit. So now if we are talking about the parallel circuit, then in parallel circuit also there will be some condition, and which is known as the resonance condition. So to understand the concept of resonance in parallel circuit, we have to consider one parallel circuit. So when circuit is known as a parallel circuit, whenever there is one inductor and capacitor is connected in parallel to each other. So let's take one circuit here. In this circuit you can see that one inductor and one capacitor is connected in parallel to each other. With inductor there is one resistor R. So that means you can say that it is the internal resistance of that inductor. And we have taken pure capacitor, so we have not mentioned internal resistance of capacitor. So basically there are three elements R, L and C, but they are connected in parallel. So in the first run there is inductor L, and in the second run there is capacitor C. Now we have to apply some source of energy to this circuit, and we have applied AC voltage source V to this circuit. And due to this voltage V, I is the current flowing through this circuit. And we know that the current flowing in series circuit will be same through all the elements connected in series. But in case of parallel, the current flowing through each element will not be same. So we have to define two different current in this both the branches. So IL is the current flowing through the first branch, and IC is the current flowing through the second branch. IL means current flowing through the inductive branch, and IC means current flowing through the capacitive branch. So now let's draw the vector diagram for this parallel circuit. So if you want to draw the vector diagram for this parallel circuit, then you have to take voltage as a reference, because in case of parallel circuit voltage is same. So we have to take voltage as a reference. On the voltage line we have to draw two different currents. One current is IL and another current is IC. Now we know that in case of capacitor, current leads the voltage by 90 degree if it is a pure capacitor. And here we have taken pure capacitor, so we can say that, so we can draw current IC exactly 90 degree leading from this supply voltage. So you can see IC current of the second branch which is leading from the supply voltage. Now let's talk about the first branch current, that is IL. So this is not pure inductive circuit. This is RL circuit. And we know that in RL circuit, current lags behind the voltage by 5 degree, because this is not pure inductive circuit. So if current is lagging, then we have to draw that current below the reference, and our reference is voltage. So we will draw IL current below the reference by 5 degree. So you can see that IL is drawn the downside of the reference by 5 degree. Now this IL is having two components. One cos component in the side where it is making angle, and another component is sine component 90 degree from the cos component, because any vector can be resolved into two components. So the cos component will be on the same side as the reference, and it is given by the IL cos phi, and this current component IL cos phi is in phase with voltage. And another component which is IL sin phi is drawn the 90 degree from the cos component like this. So this component is IL sin phi. So now we will not talk about the current IL, but we will talk about two components of that current, that is IL cos phi and IL sin phi. Now this is the same condition occurred which was occurred in series circuit. In series circuit, VL and VC was 180 degree out of phase, and in this case current IC and IL sin phi, component of that current IL, is 180 degree apart from each other. So if this two current is having the same value, then only one current will available, and that current is IL cos phi, and that current is in phase with the supply voltage. So we can say that the resonance condition in any circuit is nothing but the phase angle between voltage and current becomes 0. That means power factor of that circuit becomes unity. So this condition is only known as the resonance condition in any type of circuit. So to find the resonant frequency, because this IC and this IL sin phi is function of frequency obviously. So if you want to make resonance condition in this parallel circuit, then you have to find the frequency at which this IC becomes IL sin phi. So we have to compare these two quantities as IC is equals to IL sin phi, and we have to derive the equation of resonance frequency like this. So if we take IC is equals to IL sin phi first as a condition of resonance, and if we put the values of IC, IL and sin phi, so it will be IC is equals to nothing but V upon XC. IC is equals to V upon XC. IL is nothing but V upon Z, or you can say V upon Z, because you cannot put V upon XL, because in the first branch there is a resistor and also inductor, so you have to put V upon Z. And in place of sin phi, we know that cos phi is always resistance upon impedance, but sin phi is always reactance upon impedance, and this sin phi is only related to the first branch. So the reactance of first branch is XL and the impedance of the first branch is ZL. So now we have equation as VC upon XC is equals to VL upon ZL into XL upon ZL. So this VC and VL is having the same amount of voltage as the supply voltage. So this VV can be cancelled out. And if we make ZL on one side, then it will be ZL square is equals to XL XC. So this ZL square is equals to XL XC is known as the condition of resonance in any type of parallel circuit. Now we want to define the resonant frequency. For that we must have to put the values of XL and XC in this equation. So if we are putting the values of XL and XC in this equation, then it will be ZL square is equals to 2 pi FL into 1 upon 2 pi FC. So this 2 pi F will be cancelled out. So the equation will be ZL square is equals to L upon C. So to find the resonance frequency, still we have one term, that is ZL. So let's put the value of ZL in this equation, because we know that ZL square is equals to R square plus XL square. So we can directly put this equation here, that is R square plus XL square, and instead of XL square we can put omega L square, or you can say omega square L square. So now we have equation as R square plus omega square L square is equals to L by C. So now if omega square L square will be on one side and this R square is taken on the another side, then it will be omega square L square is equals to L by C minus R square. And if we are taking this L square on the RHS, then it will be omega square is equals to 1 upon L square into L by C minus R square by L square. So this 1L will be cancelled out and it will be 1 upon LC minus R square by L square. So now we have the omega square. Now if you want to find the value of the resonance frequency, then you have to put the omega is equals to 2 pi F in this equation. So if you put omega square is equals to 2 pi F square in this equation, then it will be 2 pi F square is equals to 1 upon LC minus R square by L square. If you are taking 2 pi square on the another side, then it will be F square is equals to 1 upon 2 pi square, and in bracket it will be 1 upon LC minus R square by L square. And if you are taking square root of this equation, then it will be F is equals to 1 upon 2 pi under root 1 upon LC minus R square by L square. So this equation is known as the equation of resonance frequency in any type of parallel circuit. So this was the resonance frequencies equation. If we neglect the resistance, internal resistance of inductor, or you can say if internal resistance of inductor is having very less value, then we can neglect R by L, then the equation will be same as the condition of equation of the resonance frequency in case of series circuit. and the equation will be F is equals to 1 upon 2 pi under root LC. So this was all about the equation of resonance frequency in parallel circuit. Now let's define the impedance. What will be the impedance at point of resonance condition in parallel circuit? We have seen that in case of series circuit, impedance was Z is equals to R. Impedance was minimum. But in parallel circuit, what is the impedance? So to find the impedance in parallel circuit, we are using another equation. And that another equation is at resonance condition, the supply current becomes only IL cos phi, because earlier current was having three components. One component was IC, second component was IL cos phi, and third component was IL sin phi. But we have seen that IC and IL sin phi has cancelled out each other due to 180-degree difference. So now our supply current I will be only IL cos phi. So to find the current at resonance, or you can say that to find the impedance at resonance, we are using this equation I is equals to IL cos phi. Now let's put all the values in this equation. Now this current I is the total current to this circuit. So the equation of this will be V upon Z, where Z is the total impedance of this circuit. Now next is IL cos phi. Again, IL is nothing but the current flowing through the first branch, and it is given by the value V upon ZL. ZL is the impedance of the first branch. Into cos phi, we know the value of cos phi is R upon ZL. So V will be again cancelled out. We want to find the equation of Z, impedance at resonance. So if we make subject Z from this equation, then Z is equals to ZL square upon R will be the answer. And if we put the value of ZL square in this equation, and value of ZL square is nothing but L by C. So the impedance at resonance will be L by CR. So this is nothing but the impedance in parallel circuit at resonance condition, and it is given by the formula L by CR. So we know that current is having the equation I is equals to V by Z, and the impedance L by CR is having the high value, because in any type of circuit L by C ratio is always taken high. So if L by C ratio is high, then this impedance at resonance will be very high, and if impedance is high, then we can say that current at resonance condition will be minimum. So this current I is equals to V by Z, and current will be minimum in parallel circuit. So this was all about the impedance in parallel circuit at resonance condition. Now let's talk about the Q factor. And here the Q factor is nothing but the current magnification. At parallel resonance, the supply current becomes small, but current flowing through both the branches is having the higher value than the supply current. This is not possible in any type of electric circuit, but it is possible if resonance condition occurs. In previous video, in RLC series circuit, voltage was maximum across the inductor and capacitor, and here current is maximum in both the branches than the supply voltage. So the Q factor is equals to IC upon I. So if we place the value of IC and I in this equation, then we know that IC is equals to IL sin phi, and the supply current I is nothing but IL cos phi. So if this IL is cancelled out, then it will be sin phi upon cos phi, and this sin phi upon cos phi is nothing but tan phi, and this phi is the angle of the resistor and inductive branch only. This is not the resultant angle of whole circuit. This is the angle of first branch, and this tan phi. So this tan phi is having the equation as XL by R, and this XL by R is nothing but omega into L by R. So if you put the value of omega L in this equation, then it will be 2 pi FL upon R. Here 2 pi L by R is constant, so only you need to put the value of the resonance frequency in this equation. So if resistance is neglected, then you can put the equation directly in this equation as 1 upon R under root L by C. So if you put this equation in the Q factors equation, then finally Q factor is having the value as 1 upon R under root L by C. So this is the same equation as we have derived in case of the series circuit. So now let's draw the graph of resonance in any parallel circuit. But to draw the graph in parallel circuit, we must need to understand two terms. And that two terms are the admittance and impedance. In case of series circuit, impedance can be directly added. But in case of parallel circuit, impedance cannot be added because the equation is 1 upon Z is equals to 1 upon Z1 plus 1 upon Z2. So we are taking inverse of that impedance and it is known as the admittance Y. So Y is equals to Y1 plus Y2. Now admittance can be added directly. So that means we have to convert all the parameter into admittance. Previously, impedance was having two terms, one real part and one imaginary part. The real part was known as the resistive part and imaginary part was known as the reactive part. Similarly, in this case of admittance, here also there are two parts. First part, real part is denoted by the G and it is known as the conductance, real part. Imaginary part is given by the B and it is known as the susceptance. If BL is given, then it is known as the inductive susceptance, and if BC is given, then it is known as the capacitive susceptance. So now let's draw the graph of resonance in parallel circuit. So to draw the graph, again we have to take two axes, that is the x-axis and the y-axis. On x-axis we will take frequency because this all phenomena is related to frequency. This all phenomena occurs due to the change in frequency. So if frequency is taken on x-axis and all other parameter is taken on the y-axis, then first we need to draw the graph of conductance G. So we know that this is a real part, it is not having any dependence on the frequency of the supply. So this conductance G will be having a straight line, having some magnitude, as similar to resistance we have drawn in the series circuit. Now let's talk about the inductive susceptance BL. So BL is inversely proportional to the inductive reactance XL. So XL was directly proportional to the frequency, but here BL is inversely proportional to the frequency. So that means at zero frequency, inductive susceptance will be high. And as frequency increases, this inductive susceptance will decrease, and at a higher frequency, this inductive susceptance becomes zero. So we can draw the graph of inductive susceptance like this. So this is the graph of BL. Now let's draw the graph of BC. This is nothing but the capacitive susceptance, and this is also the inverse of the capacitive reactance. Previously, capacitive reactance was inversely proportional to frequency, but here the capacitive susceptance will directly proportional to the frequency. So that means if frequency is 0, then capacitive susceptance will be 0. As frequency increases, capacitive susceptance will increase. So this was all three parameters, that is conductance, inductive susceptance and capacitive susceptance. Now after drawing these three components, we must need to draw the admittance of the circuit. And we know that admittance of the circuit Y is equals to under root G square plus either BC minus BL square or BL minus BC square. So we need to draw the admittance Y. So you can see that at starting condition, here BL is having the high value and BC is having the zero value. So the inductive effect will be moved. So if you want to draw the graph of admittance, then the graph of admittance will start from the infinite, because this BL is having the infinite value and this BC is having the zero value. Then as this BL decreases and BC increases, this graph of admittance will start decreasing. At some point where BL and BC intersect each other, at that point resonance occurs. Because if BL and BC is cancelled out, then circuit will behave like a pure resistive circuit. And this condition is only known as the resonance condition in any type of circuit. So the graph of this admittance will touch at the point on the resistance line where this two susceptances having the same value, that is BC is equals to BL, and it is touched on the conductance line G. And again, as BC increases but BL is again decreasing, but our graph of admittance will again increase. So we can say that the graph of impedance in series circuit and graph of admittance in parallel circuit is having the same manner. Now we need to draw the graph of current, and we know that at resonance condition current becomes minimum, and we are having the equation as I is equals to V by Z, but 1 upon Z is Y, that is the admittance. So we can say that the graph of current will follow the same line as the admittance has followed, because current is directly proportional to the admittance. Means if admittance is high, current will be high. If admittance is minimum, current will be minimum. So at resonance condition, you can see that admittance is minimum and current is also minimum, and you can say that impedance is maximum. So now if we talk about the power factor, so at resonance condition power factor will be 1, or you can say that unity. Before this resonance frequency, the inductive part was major, so we can say that the power factor will be lagging. After resonance frequency, capacitive part is more, so we can say that power factor is in leading. So in this way you can draw the graph of power factor also. So this was all about the resonance condition in parallel circuit. Thanks for watching this video. Stay tuned.